More than a million people die each year due to car accidents, and a vast majority of these accidents are caused due to human error. In 2022, around 5,800 trucks were involved in fatal crashes in the US alone. Roughly 500,000 truck accidents occur each year in the US. What if we could address this problem? What if we made our highways safer and long haul transportation reliable? Aurora is on a mission to address this challenge. In today's episode, we'll decode Aurora's journey and the underlying technology that enables autonomy for long haul transportation networks. The product that Aurora is trying to deliver is Aurora Driver. It's a combination of softwares, sensors, and hardware necessary to support a truly autonomous vehicle. Aurora was founded in 2017 by Chris Thompson, Sterling Anderson, and Drew Bagner. They saw an opportunity to build technology in a way they thought was right. So the journey began with developing the Aurora Driver, which is essentially a software and a hardware stack that could be mounted on any vehicle from cars to trucks to bring autonomy to life in a seamless manner. To do so, the team at Aurora first retrofitted a Lincoln MKZ vehicle with sensor stack and computer. With the help of experienced drivers, they then mapped city streets and developed a self-driving navigation system. This system was tested with humans behind the wheels, and it has now become a part of its autonomous driving technology called Aurora Horizon that powers long-haul trucks of Aurora. Over the period of last 8 years, Aurora's trucking product called Aurora Horizon has come a long way. Aurora is helping FedEx and Uber Freight deliver goods across North America. The hardware system built by Aurora is both robust and versatile such that it can be integrated with customer vehicular platforms like Toyota Sienna as well as long-haul trucks. Both these platforms use the same set of sensor pods and computers. Sensor pods contain powerful high-resolution cameras, long-range proprietary LiDARs, and imaging radar that can see through diverse weather conditions. To ensure these systems are robust enough, Aurora has developed in-house simulation tools to test the autonomous navigation system across both the platforms. A common virtual driver system such as one developed by Aurora has the potential to transform how goods and people move across cities. That brings us to this question: how does this system work and what do we need to build a mission-critical autonomous system of this scale? Before we explore Aurora's autonomous system architecture, let's review our standardized system architecture for autonomous systems, which includes 4 key components. The first component is perception. This includes a range of sensors and algorithms that allow our vehicle to map its surrounding, detect objects, lanes, and pedestrians, and generate a 360-degree view of its environment. The second component is localization. Localization module acts as the vehicle's compass, allowing it to track its position in the world. GPS alone is not enough since we need centimeter-level accuracy for autonomous driving. So, GPS data is combined with HD maps to ensure precise location tracking. The third component is Path Planner. This module defines our trajectories, ensuring they are safe, legal, reliable, and optimal. Motion control is where we take the trajectory from the path planner and execute it using steering, acceleration, and brakes. Now that we understand the standardized system architecture, let's take a look at the Aurora's autonomous system architecture. We cover this technology and similar case studies in great detail in our course on self-driving cars. From Zoox to Waymo and Tesla to Cruise and Nvidia, we break down the self-driving tech stack of these vehicles in an easy-to-understand manner. Ready to start your journey in this field? Check the link in the description below. Now let's get back to Aurora. The goal of Aurora Driver is really to combine the hardware and software system to enable robust autonomous navigation on highways and city streets day and night and under all traffic and weather conditions. This is possible with a custom-designed hardware and sensor configuration that goes hand in hand with the software stack that powers the fleet of autonomous navigation system. To build a robust autonomous driving system, Aurora has developed a system architecture that consists of 5 key components. This includes perception and mapping, localization, motion planning, simulation and testing, motion control. Now let's decode each of these modules one by one. Aurora's perception stack is powered by high-definition cameras, proprietary LiDAR system, and a long-range radar system. These sensors are housed in a custom-designed enclosure called sensor pods, which allow for efficient operations for long-haul missions. Specifically, it includes a radar system, high-definition short-range and a long-range camera system, and a long-range LiDAR system. This powerful multimodal sensor suite provides 360-degree coverage at both short and long ranges at all times during day and night in all traffic and weather conditions. Aurora uses a proprietary FMCW LiDAR system that is not only immune to interference caused due to sunlight, but also is robust enough to withstand interference caused due to nearby sensors. It can measure both distance of nearby objects and their velocity with the highest levels of precision. LiDAR, which stands for Light Detection and Ranging, uses laser pulses to create highly accurate 3D maps of the truck's surrounding, enabling precise object detection, distance measurement, and environmental modeling. Its ability to operate in varying light conditions makes it a key component in pursuing obstacles and road geometry during day and night conditions. Radar, which stands for Radio Detection and Ranging, uses radio waves to detect objects and measure their speed, distance, and direction. This system works even in poor visibility conditions like fog or heavy rain. Hence, radar works in all weather conditions and excels at tracking moving objects such as vehicles or pedestrians, making it crucial for collision avoidance. High-definition cameras capture detailed visual data, recognizing traffic signs, lane markings, and color-coded signals, which are essential for contextual understanding of each scene. They complement LiDAR and radar by providing rich visual information for object classification and scene interpretation. The data from these sensors is fused using sensor fusion algorithms to build a coherent 3D view of the surroundings. If we dive deeper, the data from these sensors is processed to produce three distinct outputs. The first is the Euclidean view, which represents a 3D point cloud. The second is the range view, a 2D map, and the third is the image data consisting of raw images captured by our cameras. This data is then processed through layers of artificial neural networks in a continuous manner to fuse these inputs and generate a unified 3D view of the truck surrounding. The output from the deep learning or the neural network layer is essentially a coherent real-time projection of sensor data on a 3D map of the truck surrounding. Aurora uses its test fleet equipped with the same set of sensors that are used on its trucking system to map major highways and long-haul routes around the US. This mapping system is known as Aurora Atlas. They have developed these maps from ground up to ensure cost-effective operation in the long run and provide accurate pre-recorded maps to customers at scale for long-haul missions. Once the maps are created, we can match real-time sensor data with the pre-recorded map data to identify points of maximum alignment. This helps us determine the truck's precise location. While there are several methods to determine a truck's location, this is one of the most commonly adopted approaches in the self-driving industry today and is known as map matching technique. So far, we have covered the perception and mapping system that enable the development of 3D maps of the truck surrounding. We then explored the localization module, which uses map matching techniques to determine the truck's precise location. Now we need to identify the best cost path to navigate our truck from its source point to the destination point. And that's where the motion planning module comes into picture. The easiest way to understand the motion planner is to know that we are trying to answer a fundamental question. Given the state of the world around the truck as sensed by the sensors and cameras, what is the action we should take? So, this question is modeled as a mathematical function which takes into account the current state of the agents in the scene, that is S on the left, and the action that we need to take in order to navigate safely in this environment. The challenging part here is that our action not only depends on the current state of the nearby agents on the scene, such as cars and pedestrians, but also their future state. So now we need to first predict their possible future states and then make a decision. To accomplish this, we first use our standard perception system made up of LiDAR, radar, and cameras to identify the current state of the agents in the scene. We then use standardized probabilistic functions, essentially Markovian models, to predict the next most probable state for the core agents in the scene. In this case, it's the vehicle that is about to merge. We then develop trajectories or plans for our truck using these forecasts. This happens at an unprecedented scale and speed using the rich data we receive from sensors and the underlying neural networks that process this information and develop trajectories in real time. For scenarios that cannot be easily predicted or managed by the navigation system, an alert is sent to the teleoperation team. The team takes control of the vehicle, assesses the situation, and makes a decision that is safe, reliable, and robust. To ensure the planner can handle a wide range of scenarios, the team at Aurora simulates these driving situations using their in-house simulator. This simulator precisely simulates both the output of the sensor system and the traffic patterns. This team tests the forecasts and the trajectories predicted by the planner across thousands of scenarios under diverse traffic and weather patterns using this simulator. This ensures that the system is fully capable of autonomously managing the vast majority of scenarios with minimal need for teleoperation during long-haul missions. An interesting point to note over here is that Aurora simulator can simulate in 1 hour the equivalent of over 50,000 trucks operating simultaneously on real roads. Simulators enable self-driving systems to be trained at scale, making them highly effective for long-haul missions. The trajectories finalized by the simulator are executed using the motion control system, which considers the current state of the agents in the scene. Essentially, the motion control system activates steering, brakes, and accelerator to execute these trajectories. That essentially summarizes the system architecture of Aurora's self-driving system. We cover this technology and similar case studies in great detail in our course on self-driving cars. From Zoox to Waymo and Tesla to Cruise and Nvidia, we break down the self-driving stack of these vehicles in an easy to understand manner. Ready to start your journey in this field? Check the link in the description below. Thank you.